3:30 now, so any second when we're ready. Go.
Okay, I'm Tracy Jakewith. I work at the Internet Archive. I am the second longest standing archivist, so how about that? Today we're going to have a 30-minute talk titled New Primitives for Cryptographic Protocols. I know all the words, but Bram Cohen is going to make it all work and explain it to us. Take it away.
Hey everybody. So I'm Bram. I've done some peer-to-peer stuff in the past, and now I'm working on a new cryptocurrency called Chia. This presentation is not going to be on Chia. This is on some stuff we've working on as part of building Chia, which is much more widely applicable than just us. So I'm going to be talking about two types of primitives: BLS signatures and verifiable delay functions. And as of like an hour ago, we have now made our BLS library available. It's on GitHub. It's in the URL here that you can see. So at a high level, BLS signatures are sort of like Schnorr signatures. So Schnorr signatures are this hot thing that people are excited about in Bitcoin land because they support aggregatable signatures. And BLS signatures also support aggregatable signatures, except they support non-interactive aggregatable signatures. So I'll get into what that means. At a high level, it means that if you have a bunch of signatures and you don't have the access to the private keying material, you can still glom them together to make a combined aggregate signature. So in the code that we have here, this is showing here I'm going to make a public key, a private key, and then generate its public key, and I'm going to make a signature out of it. What? You want me to do this? So that's so far so normal. You then serialize it. I'd like to point out an interesting design decision we made here is our public keys are 48 bytes and our signatures are 96 bytes. This is the opposite of how people usually do stuff when you're doing public key cryptography. But there's this interesting thing when you're doing cryptocurrencies, in particular with aggregatable public keys, that your public key is used once and it's used to sign a very small fraction of one thing because all your keys are aggregated, all your signatures are aggregated. There's essentially one signature in every single block, and that's it. So it frees up a huge amount of space in your blocks and creates this design decision where we have 48-byte public keys and 96-byte signatures. We're actually being extremely conservative as opposed to the BN128 curve, which has 32-byte public keys, but we're being super, super conservative about decisions here. All right, so once you have a signature, somebody else can then take the signature and deserialize it, as is shown. And then you can verify it. Interesting subtlety here to this API is you need aggregation info. So you need to tell it when you have the signature, you have not only the signature itself, but you have this is the public key that was signed and the message that was signed. This is important. This complexity was added to the whole thing because we can aggregate things. So this example here is about aggregating a single message. This is very magical. What's happening here is then you signature look like totally normal, valid public key signature pair for that message. There's no way of telling that this was done to generate this, which is a really magical thing to have happen. This enables a few things. It enables very simple custody arrangements where you're not leaking the fact that you did this custody arrangement in the public information on the blockchain, and you're also saving space on the blockchain. And also, if you're doing lightning channels, it makes it so there are tricks you can pull off such that there are tricks you can pull off such that your channel open and closes in Lightning look like totally normal, simple transactions because you're using this kind of trickery there. It's also possible to do M of n. This is n of n. You can also generalize this to m of n, which we haven't finished writing yet. That's not quite as stupidly non-interactive as this is, but also definitely works.
This is not quite as
stupidly non-interactive as this is. That involves slightly more complicated message flows, where this one the message flow is all the signatures are just sent to whoever and they just combine them. M of n, you have to do more stuff. Okay, so that enables some really fun things. You can also do a different type of aggregation where you're aggregating basically all the messages for a transaction or all the messages for a block or something like that. So you have multiple signatures of different messages. So here we have this. And then you combine them. Yeah, you make your signatures, combine them together, and then you make the serialized message. You then, this is actually doing a slightly complicated case to make a point. You can then verify this. There's a little bit of a subtlety that you have to remember how the aggregation was done. So under some circumstances, you have to leak some of that information. Sometimes you can simplify it, sometimes you can't. But you remember how the aggregation was done, and you still have just one signature. So in this case, you had 3 things, and somebody aggregated the first 2, and then somebody else aggregated the aggregation of those 2 with a 3rd thing. And this is an example of then verifying that combined aggregated signature. So because this supports aggregates of aggregates and stuff, it enables you, if you want to use this in a cryptocurrency, you can reliably, always, never making any weird exceptions, take all the public key signatures of everything happening in that block and just make a single 96-byte pub key. You just have to make sure that the aggregation info is implicitly kept. Is the only little caveat there. Another little trick here is that the private keys in that n of n thing that I said, the private keys aggregate as well. That if you aggregated the private keys and then signed directly with the aggregated private key, it would produce the aggregated public key, the aggregated signature directly. Yes?
So if I understood the previous example, you're taking 2 separate texts that were signed but with the same signature and aggregating it into one signed text.
The last example that I gave, is very, very general. You can have 2 different texts that were signed with 2 different signatures, and that can be aggregated together.
So let me tell you the concern that I want to raise here.
Yes.
To understand if it's a genuine concern.
Yes.
If let's say I, with my signature, sign text A,
yeah,
and then I separately sign text B,
yeah,
it might be that A and B as separate texts signed by me are taken to mean one thing, but had I signed the concatenation of them, it might be, had I signed the concatenation of them as one signing event, it might be taken to mean something else.
We are using a construction from some of their advisors at Stanford, which is linked to on this page that makes all this stuff secure. So we've fixed everything. There are neat things you can actually do from a smart transaction standpoint, even with this. It doesn't just save you space. If you have, for example, a transaction that doesn't have a high enough fee, because someone basically gave you this transaction, and they figure it's your job to pay the fee. And you happen to not have published this yet, so no one else knows this, the transaction. A trick you can do, because the fee on this first thing wasn't high enough, is you can glom this transaction together with another transaction that's totally unrelated, that has a high enough fee for both of them put together, and make it so other people can't split them apart again because you just give the aggregated signature of both of them. And other people can't split that apart into 2 signatures unless they have one of the original ones. And now you've done like peer pays instead of child pays, is kind of a neat trick.
Thank you.
But yes, the short answer about any security questions is we have magic pixie dust that fixes all security concerns. It would have been nice to not have people have to remember exactly how they aggregated everything together. That actually is necessary for security reasons because of rogue public key, blah, 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 blah stuff. So we were worried that that would have more significant impacts on it. Turns out you just have to remember some metadata and leak that information a little bit sometimes. Rogue public keys are if you screw up your construction and you allow multiple pub keys to sign the same message and you don't do it right, there are ways people can fake other things having been signed in the aggregate signature. Did you say why you wanted to aggregate private keys? Aggregating private keys isn't super necessary for any protocol I know, but it's a neat trick. It only works, the aggregating private keys only works for the N of N trick. But that particular one is extremely magical, so that's just a fun thing. Yes?
Are the aggregations all like A plus B and B like A plus B plus C?
You can aggregate together any amount of stuff, and you can aggregate aggregates and aggregate aggregates of aggregates and everything. It all works magically. It all has fixed size signatures at the end of the day. The only caveat, I keep saying, is you do have to remember how it is that you aggregated everything together. There are some tricks you can do if you have an absolute guarantee that no 2 of the signatures are on the exact same message, then you can flatten out your aggregation info into just a single list at the end of the day, and it will still verify. And we have other stuff here. There's more. We support HD keys. So HD key, this is hierarchical deterministic, which is used for wallets in Bitcoin. And we have a thing where you can extend your, you can take a private key and make a child private key. And you can take a public key and make a child public key, and they still correspond to each other. This is how Bitcoin does wallets. This is the thing that enables the feature where you can just keep handing out different pub keys to everybody when they ask you for a target, and your wallet easily remembers all of them. And so we've supported this feature now. So we're pretty feature complete as far as BLS signatures go. So this is now available. People can go play with it. The downsides are mostly, pub keys are a little bit bigger, or technically, order of things is weird. The main complaints people have made about this are it makes some extra security assumptions, which aren't really scary at all. And we're being extremely conservative, like I said, about our choice of curve here is way excessive. And the main other problem is doing the verification operations is slower than doing verification operations for libsecp by a factor of 7 or something like that.
Which curve?
Libsecp is a specific curve. It's the secp curve. Libsecp is the thing that's used in Bitcoin. There are subtleties about whether you flip the curves around and blah, 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 blah stuff. So I'm just repeating a headline number that I know, so I can't give more color on exactly what the comparison is there. But it is the case that doing these BLS operations is slower. It is my belief that that is way more than made up for by the compactification on the blockchain and the additional smart contract functionality that it allows, and how easy it is to implement everything because you have these non-interactive aggregations and you don't have to remember all this metadata. So you can go play with this right now. Invite feedback from the community. It's on GitHub. So other thing I wanted to talk about, if that wasn't enough for you, for verifiable delay functions now, not quite ready to show it to everybody. There will be another release of that in the future. All right, so what are verifiable delay functions? Verifiable delay functions are this magical construction that people have actually wanted for a really long time. There were time lock puzzles that were invented like more than 20 years ago that are a closely related primitive where like I want to send you a message and I want to say, okay, I'm going to send you this message, but you can't unlock it for the next 20 years. So I make it so that there's some operation you have to do that's going to take you 20 years to do to unlock it, but I have a shortcut where I can calculate the thing quickly myself. And frustratingly, everybody, and I mean everybody, including me, came up with the exact same construction for time lock puzzles. And there wasn't much of any improvement on it. And with the recent motivation that's caused it, there was a paper in Eurocrypts that got best paper that was on VDFs. There was another paper that is in crypto by Dan Bonnet et al., which is another really great construction, which we're also not using. We're using a newer construction than that. So this is all very, very new and exciting stuff. So what are proofs of time? Proofs of time is very much like a time lock puzzle. It demonstrates that some amount of time has passed between when the challenge was issued and when the result was found. This is useful for a few things. I'll explain one of them in a minute. The important thing is that it's non-parallelizable. So there are some things that kind of work for this but are really terrible, like repeatedly hashing SHA-256. You have a hash of a hash of a hash of a hash and so on, k times, where k is some proportion to the amount of time you want to have passed. That is, technically speaking, a proof of time. It's just hard and annoying and awful to verify that the output is correct. What you really want is that to have a nice succinct proof that the output of this is valid. So the new results are actually all related to the old proofs of time, or not, to the old time lock puzzle stuff. It's actually using the same underlying construction as the time lock puzzles use, which is you have a group and you have a generator and you need to find the generator to the 2 to the k, which you find by squaring the generator k times. So that's the sequential thing that you do. And the thing that's new is that, do I say this next time? Okay. The thing that's new is that we now have succinct proofs of the validity of these things, which whoever it is that's doing the repeated squarings can generate fast, even though they themselves don't actually know what the order of the group was. So that's the new and exciting stuff that's happened. I'll get into more of that in a minute. First, I need to explain what on earth would you do with such a thing. Let's say that you have a lottery. You have 1 million people participating in a lottery, and they all put in $1, and the winner gets all the $1 million. And you want to make it so that they all can audit that this was done fairly, meaning actually randomly, and no one party has the ability to manipulate who it is that won. This is a very, very hard problem to solve using multi-party computation stuff. Extremely difficult, but if you have a VDF, you can totally cheat. So if you have a VDF, what happens is randomness, their entropy, and they submit it, your data, and it can be any data, any garbage data, human readable, not human readable, whatever. It's just your data that you're submitting just to make sure that you had a hand in this thing, that you somehow had some influence over who was the winner of this lottery. Verifiable delay function. It is a proof of time, is a more poetic name for it. But verifiable delay function is much more precise. It is a thing that has the properties that it requires some number of non-parallelizable iterations to compute, and that the output is canonical, and that it has a succinct proof that is quick to validate of the correctness of the output. Everyone has submitted their stuff to the collator. The collator publishes everything. And so anyone who wants to can download the whole thing, or even they just publish the Merkle root and gives everyone who submitted a proof that their thing was included in the Merkle root. And now you take the Merkle root or the entire thing and hash it up, and you are going to compute a VDF on it. We have general agreement about how fast the VDFs run. We assume that we have this, give or take an order of magnitude. And we say the VDF is going to have to run for a day. from the end of the time window when everyone was submitting their stuff before we find out what the output of the VDF was, and that determines who it was that won the lottery. We use that for calculating the winner of the lottery. And now everyone can audit that their data was in fact included in this, and that it was in fact fair, and nobody, including the collator, can actually exert any control over who the winner was. Trivially, the collator can include and not include stuff. Everyone can change what data they put in. But it's all fair in the sense that no one has any idea how their decisions of the things that they have discretion over will affect what the output is, because the output is just garbage no matter what it is that you do. You can make it be different garbage, but you don't know what, so everyone knows that you didn't change it in the middle. But this works very, very well. This is great. This is totally a cheater way of accomplishing this thing that you couldn't otherwise accomplish. Sort of a silly use case, but kind of neat that you can do it. These also have other motivations. Wanting to have VDFs has actually been around for a long time. The reason there's been much more serious work on this now is that it turns out you can use them for securing blockchains. So at Chia, we have a bunch of advisors, and I've been haranguing them to work on this stuff. If you want to make a blockchain based on proofs of space, there are a lot of problems with this. You can fix them using proofs of time. That's way beyond what I can explain in just a few minutes. If you go to chia.net, there's some talks that sort of kind of cover it. So like I said, the new constructions require that you have groups which nobody knows the order of. There's a few ways of finding these. The obvious way is you do trusted setup of an RSA group. That kind of sucks. You need trusted setup. You can't change your group on the fly, which you would really like to dynamically use a new one every single time. So we're going with class groups. Raise your hand if you know what a class group is. That's what I thought. OK. Nobody knows what a class group is. I didn't actually know either. They're something in number theory. Gauss studied them. We are doing the first ever deployment in industry of class groups. So we're going to have a write-up of, we are soon releasing code for this, not quite yet, not quite ready yet. We are going to be releasing supporting materials, including a really nice write-up of what on earth class groups are that you can read with only high school math background, sort of on the level of explaining complex numbers, a little more complicated than that. But that's really fun. And if in the next couple of weeks you're really excited about this and feeling really ambitious, you can read these papers that are on the web right now. The first two are new constructions for succinct proofs. The third one analyzes the first two. At Chia, we're going to be using both of these for various and sundry reasons, actually, because they work on the exact same underlying construction. They're just different types of proofs for it. And if you really, really are ambitious, you can actually read about class groups. There's a Wikipedia page about them. It's a little mathy. All right, and that's all the new stuff I wanted to cover. At Chia, we're going to be doing more stuff. There's going to be proofs of space as another new primitive and other things that we're working on. That code is also not available yet, but that's where we are right now.
Great talk. I honestly didn't understand a whole lot of that, but we've got a few minutes for questions, so be the mic runner. If you've got your hand up, I will get you the mic.
I missed it. What was the advantage of the class groups over just the
the advantage of the class groups is that nobody knows the order. If you know the order of a group, you can short circuit the VDF. So you want a group where you know that nobody knows what the order is. And class groups are a good fit for that. And it's an extremely weird property to have that's a problem for many things and is a feature here. And no one had a use for that in the past, but now we do.
So in fact, nobody, it's hard to
there is no known efficient way of calculating the order of a particular class group.
So does that just mean you have to discover the order like by going through it and then finding out?
The order is like 1,024 bits long. You're never going to find it just by iterating through it. There are much more efficient algorithms than that for calculating the order, but they are still, like to the 256 or something kind of scale of difficulty of finding it. And what the actual computation you're trying to do, you can do rather fast because you just do the intended computation and it takes 5 minutes.
So nobody knows, including you.
Yes, that's correct. You do this thing where you take your challenge and you generate a random prime using it that's long enough and use that, the negative of that is the discriminant in your class group, and this is something that nobody knows what the order is.
Thanks.
Okay, maybe 2 more questions.
So what's the difference between this, between a proof of time and a proof of work? Or computation?
So a proof of time is a strange and interesting type of proof of work that's non-parallelizable. Like general proofs of work, you can set up as many CPUs doing as many of them as you want. So the amount of work you'll have demonstrated at some point is the number of CPUs you dedicated times the amount of time you ran them. And for a proof of time, it doesn't matter how many CPUs you're running, they're going to take the same amount of time to generate the exact same output. So it is in that way, yeah, but it's sequential, it's non-parallelizable, and that's the key to how it is that like a proof of space-based system can be much less wasteful because it's leveraging just the storage and does not have any particular advantage for extra CPU.
Is this safe against quantum? In particular, if quantum breaks both discrete log and factoring, does that enable one to short-circuit the sequentiality? To calculate it in less steps?
In principle, quantum secure is not so much an either-or thing. In principle, there are quantum attacks on finding the order of class groups that are fairly powerful. However, for the particular calculations, at least for Chia that we're planning on doing, you have 5 minutes to do it. Like literally, the only thing this is ever going to be used for is something that will be done over with, never to be changed again 5 minutes from now. And because of that, it would not need to not just be a quantum break, but an unbelievable quantum break to actually break the primitive.
All right, we're out of time. Thanks a lot for the talk and discussion and questions.